So in part 3 video, we left it off with just kind of through playing, through observing, through looking for patterns, looking at Desmos, we saw that this function n squared plus n has factors of whatever you input n times one more than n. That's always true. And that was kind of easy to see because I picked an example here to start with where you could easily see that one input was n, or one factor was n, and the other factor was one more than n. But what if the relationship wasn't so easy to find? What if the factors were a little wonkier than that? Then what would you do? Well, I want to show you one more thing that'll help you answer that question. I'm going to show you one more thing. So what would be the easiest output to think about factors of? Like if you look back here, we had outputs of 42. Well, that wasn't too bad. Factors of 42, 6 and 7. Or we had even an output of 74.1138899. But we had seen from our previous work that the factors would be the original n times the number one more. But what would be even easier than, say, a 42 or a 20 or a 12? I argue that the easiest thing to think about factors would be 0. What if you inputted a value for n and outputted a 0? So remember that quadratic that we thought about and we've graphed now in Desmos, but here it is again. And notice there's 2 times that there's an input that outputs a 0. If you input a 0 for n, you output a 0 for the function value. Watch. If you input a 0 for n, 0 squared is 0, plus 0 is 0. So if you input a 0, you output a 0. But also, the other 0 would be if you input a negative 1. Negative 1 squared is positive 1, plus that negative 1, positive 1 plus negative 1 is 0. There are 2 values that would make that output of 0. So this is what we do. We just leverage those 2 to find our 2 factors. Here's how we do it. I'm going to bounce back to Word so I can write. So in the graph, what we found out was one of the zeros was negative 1, 0, and one of the zeros was 0, 0. That's what we call them. Where the parabola intersects that horizontal axis, we call those zeros of the function. Why? Because they're the inputs that output a 0. That's the input that outputs a 0. So it makes sense to call those the zeros, or the horizontal intercepts, if you will. But anyway, that's what we call them. So how do we use them to find our factors? Well, here's how. So if our original function was n squared plus n, and we want to write it as the factors of 2 numbers, what would those 2 numbers be? Here's what they would be. So the first one would be n minus the first 0. Now, that doesn't have to be the first one. It doesn't matter what order you put them in, but I'm picking this one first. And the first one would be 0 times n minus the second 0. And the second 0, notice, is a negative 1. And notice when you do that, n minus 0 is n, and n minus a negative 1 would be n plus 1. And there's the 2 factors that we had seen earlier. The 2 factors were the original n, and then one more. So we can find those factors easier by just looking at the zeros and then kind of thinking through what the 2 factors would be to produce those zeros. Notice that when n is 0, 0 times any other number would give me a 0. And when n is negative 1, negative 1 plus 1 is 0, and that would make the entire product 0. So there's 2 values for n, 0 and negative 1, that make the function output a 0. Therefore, the 2 factors are n minus 0 and n minus the negative 1, simplified just n plus 1. So that's how we can easily find, more easily at least, find the 2 factors of that quadratic expression or quadratic function. All right, that one, since we've been working on this one so long, let's use that same strategy in a different case. 3x squared plus 4x minus 9. Now, before we even start, I'm going to ask you one more time to just let your brain think through what would this function look like graphically. So pause the video and think through it on your own, and then hit play again, and you'll hear me thinking through it. I hope you give it a shot. So here's what I would do first. I like to start out there with that -9 or that -9 because why? When x is 0, so we say that's the initial starting point. And when x is 0, this would be 0, this would be 0, -9 would be -9. So when x is 0, the output would be a -9. So we're going to start our parabola here. All right, now we move over to that linear part. Remember that the linear coefficient there is the initial rate of change, initially starting from that 0, -9 point. So 4, or 4/1, means that if you increase x by 1, you would increase y by 4. There would be our original rate of change of 4/1. But then that rate of change wouldn't persist. We would look over here at that second rate of change, the rate of change in the rate of change, and we would say, well, how is the rate of change changing? And remember, this number is half, so the actual second differences that were constant we would have seen had we done all of that work would have been a 6. And so we're going to see those rates of change get even steeper and steeper and steeper. And then remember, if you kind of go backwards, the same kind of thing is going to happen, but we have to get steeper and steeper and steeper. I'm sorry, we have to let that rate of change get greater and greater and greater in both directions. So roughly, it's going to be like this. Let me again make you see it. So here, you have a big negative, and then a less big negative, and then a less big negative, and less big. So if you're going from, I'm making this up, like -11 to -7 to -4 to -1, do you see how we're moving in a positive direction? We're moving to the right. We're getting bigger numbers from -11 to -1. And then eventually we're going to get over here to 4, and then maybe 7, and maybe 11. So these rates of changes are getting bigger and bigger and bigger due to those second differences being positive. And so the parabola we would expect to see would be something like this. And look at, there's 2 zeros. All right, back to PowerPoint or slides. All right, so I wanted you to just think through what that function would look like, and sure enough, there it is. So if you can maybe tell that there's your initial -9, there's your initial rate of change of 4, but then those rates of change are getting more and more and more and more. We're going in this direction, more and more and more negative. So there is the parabola. So now, how do we get factored form? Well, because we have Desmos, we can just click on those two zeros, or those x-intercepts, or those horizontal intercepts. We can just click on them and find out what they are. And so then we write our factored form. Remember how it looked back here? So when we had a 0, I would have written n minus 0, which is just n. And then a -1, I would have written n minus a -1, which is the same as n plus 1. Well, now what are we going to have? We're going to have I'm using x this time. I'm going to have an x minus 1.18925, and then an x minus a negative 2.52259. So x minus 1.18925, there it is, and then x minus a minus or a plus. Now, remember, in our previous case, our leading coefficient was just a 1. And so we have a leading coefficient of 1 here as well. But in this case, we have a leading coefficient of 3. So I need to continue my leading coefficient of 3. So in factored form, this would be equivalent to this. So we call this standard form when you can do that deal about, well, initially the function's at -9, has an initial rate of change of 4, but that rate of change is getting greater by 6. And we can kind of think through the parabola. In factored form, we would say x plus 2.252259 and x minus 1.18925. Now, you can go on Desmos now and kind of fact check me here, but you just have to trust me that I just changed the colors, but I really did take that function and I graphed it on Desmos to get this parabola. And then I took the factored form and graphed it on Desmos, and it's the same parabola. So that's how we get it in factored form. All right. Now, there's more to the story, but I'm going to pause here and let you think about that.